And hello everyone. You should be able to hear me now, which would be excellent if you could confirm with a thumbs up, just to make sure I can hear you. Um, and if you can hear me, excellent, thank you. So what we're going to talk about today is a continuation a little bit from last time, which is uniform circular motion, which we started talking about. And then we're going to also talk about non-uniform circular motion, which is slightly different, but of course very similar. It's still circular. And then we're going to go on to talk a little bit about relative motion, so talking about how to describe the same motion from two different reference frames. So let's remind ourselves what we did with uniform circular motion last time. Okay, this is just a repeat. So what we did with the uniform circular motion was we introduced this centripetal acceleration. The centripetal acceleration being the acceleration that in constant speed, in uniform circular motion, which has constant speed, that's the acceleration that points to the center of the circle that we describe, the center of the circle that describes the motion. And we derived the magnitude of that constant acceleration, the magnitude of the constant magnitude of the acceleration. And we actually wrote this as, so in the case of uniform circular motion, we derived that the magnitude of this acceleration was v squared, the speed squared, over the radius squared. So someone's asking if these notes have been posted. So the funny story about that is that I accidentally got unenrolled from the course on Learn myself. So I'm waiting for IT to add me. Once IT adds me, I can add materials to the course site on Learn again. Naturally, yeah. I was surprised that Learn even allows the instructor to be unenrolled from the course, but apparently it does. So let's get back here to uniform circular motion, and the centripetal acceleration, the magnitude of which is v squared over r. So we can of course use that magnitude to turn this into a vector, and we did. And the vector is of course going to be point inwards. So this gets a negative sign, a magnitude of v squared over r, and then the direction, which is along the radial direction. So we have it pointing inwards along the radial direction with a negative sign and a magnitude that's v squared over r. Often what will be so I see there's some people who are not unmuted in the class, so please mute yourself. You should be able to see a little text bubble above people who are actually unmuted. So that would help if those people can mute themselves so that there's no feedback of sound. Okay. So sorry, I don't have any way to just unmute or to just mute everyone. So that's not one of the buttons that is available to me. So I can't just say mute everyone from here. Okay. So back to uniform circular acceleration. One of the things that we'll see is that acceleration is going to be focused, is going to be often expressed in terms of gravitational acceleration. So what you'll see is, for example, that the acceleration, the centripetal acceleration, might be minus 19.8 meters per second squared in the radial direction. And that would be written also as minus 2g in the radial direction. And we would say that the centripetal acceleration is 2g, where g is of course the 9.8 meters per second squared that we used in free fall problems. So in some sense, we're using the acceleration for free fall problems as a quantity that we express other accelerations in. So think about this g as the kind of acceleration that you experience when you're just standing somewhere. We'll come back to that when we talk about forces specifically. But g is essentially the force of gravity that is working on you, and so an acceleration of 2g would be twice that size. So let's look at an example of this for uniform acceleration. I'll give you a minute or so to calculate that. So if we have a car that travels at a speed of 10 meters per second, I'm not saying this is necessarily a realistic speed and a realistic radius that I'm going to give here, but it makes the calculations easier. And this is in a curve, a circular curve, since we're talking about circular motion, with a radius of 100 meters. So if we have this problem, a car traveling in a curve with a radius of 100 meters, of course the question is now, what is the magnitude of the centripetal acceleration? So I'll give you a minute to calculate that. So when you put the answer in the chat, make sure you use the right units. Right? So if we have the magnitude of the centripetal acceleration is v squared over r, and so v here is 10 meters per second, this squared over a radius of 100 meters. So obviously that is going to be 1 meter per second squared, or if we want to put this in terms of g, this will be approximately 0.1 g. So about 1/10 of the acceleration due to gravity. And what's going to be the direction of this centripetal acceleration? So the direction will be, as all centripetal accelerations, and as actually the name implies, because centripetal means searching the center, so it will be towards the center. So this will be AC is going to be minus 1 meter per second squared in the radial direction, so towards the center of curvature of this curve. Again, pointing towards the center as here. So now that we have calculated the magnitude and the direction of the centripetal acceleration, we're also going to want to put this in terms of our position vectors, r as a function of t. We're going to want to determine our velocity vectors and our acceleration vector as a function of t, because one of the things you'll see is that this radial vector, this unit vector in the radial direction, that will of course change over time if we want to put this in x and y components. So that will be why we want to introduce this with a little bit more mathematical detail. So we're going to introduce the vectors and their x, y, and z components. So first what we're going to do is we're going to introduce the angular velocity, the angular frequency. Both terms are used. Angular frequency omega. And that is going to be the angle. Omega is such that over an interval delta t, in a time interval delta t, the particle or the object or the car in this example describes an angle omega delta t. So if omega delta t is an angle, so if omega delta t has dimensions of angle, so is essentially dimensionless. We don't think of angles as having a dimension, and delta t has dimensions of time, then omega will have to have dimensions of inverse time, right? So that's why we use omega, why we call it a frequency. Frequencies are going to be things that have units of inverse time. You can write omega however you want. You can write it as W. You can even call it W. Just know that I will call it and write it as omega, just like I will call and write alphas as alphas and so on, phis as phis. So Greek letters are going to be Greek letters in this course. And unfortunately, in physics, there are so many symbols that are often used that we have to go to entirely different alphabets and use most of the Greek alphabet and probably some of the other alphabets as well for writing the symbols. So let's think about this omega, this angular frequency, a little bit more. What happens if we pick as delta t, big T, which is the period of this circular motion? That is the time it takes to make one revolution. So then omega delta t, or omega big T, will have to be the angle over one revolution. That's going to be 2 pi. So that gives us already that gives us already one way to define omega. So omega is going to be 2 pi over the period of motion. So so for a full circular, a full revolution, one time around the circle, it takes a time t. So omega will be 2 pi over t. Now we can write the time it takes for one revolution, also using the radius and the speed, of course. So we can write the speed in particular as the distance traveled, 2 pi r, one circumference of the circle, divided by one period. So that's another way to introduce the period. And we can actually, from this, calculate that t is 2 pi r over v. And we can now plug this in here, and we can use that to calculate another expression for omega. So omega will be 2 pi over, and then we'll have t here, so that will be 2 pi r, and then a v up here. So we'll end up with v over r as the expression for omega. So a couple of formulas then. So we've got this one here for the period, and then we have omega is v over r. Now if we have omega is v over r, and remember we have AC is v squared over r, that will allow us to write this as omega times v, or even as omega squared times r, right? If we have omega squared as v squared over r squared, well, we need to get rid of one of those r's to make this equal to AC, so we're going to write this as omega squared times r. Or we could even write this as omega squared. Well, there's other ways to write this. So there's different variables, and we can of course write AC with the combination of variables that we are interested in. If we are given omega and we're given v, then we would use this part of the formula. If we are given omega and we're given r, and we're asked to calculate the centripetal acceleration, then we would use the last term on the right side here. Okay, so that gives us now omega, and so omega will be expressed in per second. Um, so there's no square root here. I don't know if you're seeing a square root. Oh, this is a letter V. That's the speed. So yeah, I apologize for my handwriting. It is my handwriting. It's not something that is easily changed, even if I sometimes maybe also wish it was clearer in class. But anyway, okay. So let's now turn that that expression of omega, and let's use this omega to introduce the position vectors. So before we do that, we have to do one more thing, and that's taking this term, which we used to calculate this angle, and turning it into an angle, a phase theta, which is going to be omega times t, and that is going to be the phase angle, sometimes just called phase, starting with theta is equal to 0 at t equal to 0. So if we go back to the drawing on the slide, if we start, I don't know if I have a better drawing here, this one here for example. So if we start with at time t0 along the x-axis, then after a time t, we'll have traversed an angle theta here that is omega times t. That's really just the same formula as the omega delta t here, except that we've now forced or theta equal to 0 to be at time t equal to 0. So in some sense, where delta t was maybe t minus t0, now we've actually forced t0 to be equal to 0 for simplicity, and just because that's how it is commonly done, because we can pick, of course, the direction of our x-axis. So now let's go back to that drawing here. You can already see what's happening here. We're at a constant radius. So the x coordinate along the direction where we were at t equals 0 will be the magnitude of this position vector times cosine omega t, and we'll have sine omega t along the y direction. So that will give us that the position vector is the radius, which is a constant for uniform circular motion, times cosine omega t, and this is along the x direction, plus the radius times sine omega t along the y direction. So all of this, omega is going to be in units per second, which is technically radians per second, or which you could think of as radians per second, but we don't consider radians as a unit. So don't plug in degrees in omega. When you take this cosine, the units here have to be in radians. Omega t will have to be in radians. And of course make sure that your calculator and so on is set to the right values. So typically what you'll see in physics is we're going to be talking about angles in radians when it's sort of physics angles, and we're going to be talking about angles in degrees when it's, let's say, the slope of an inclined plane, or something that has a very clear, unique geometrical meaning. Anything that will vary with time is typically going to be given in radians, and is going to be considered in radians only. Okay, so that's our position, the position vector, so we can use that now from this position to calculate the velocity vector. V is a function of time, which is d dt of the position vector. Now, of course, for those of you who haven't seen calculus yet, let me quickly tell you what the derivatives look like for these cosine and sine functions. So d dt of cosine omega t is minus omega sine omega t, and d dt of sine omega t is omega times cosine omega t. So that's an aside here for those of you not familiar yet with calculus. But if we use these time derivatives of the cosines and the sines, which are the only parts that are dependent on the time here, then we're going to get that the velocity is minus r omega sine omega t in the x direction plus r omega cosine omega t in the y direction. So that's our velocity vector now, as a function of the time. And you'll see you would actually be able to calculate r dot t dot product with v, r of t dot product with v of t. And what will be the value for r dot v? So you can do this mathematically, but you can also think about it. And in particular, think back of this drawing here. So we have a velocity that's tangential to the circle. We have an acceleration that is pointing towards the center. So it's going to be perpendicular to that velocity. And so if we think about that in vector terms, that means that the dot product between r and v will have to be 0. And if you calculate the dot product between r and v in these expressions, you'll see that you get exactly that. You get 0 because you'll find that you end up with a r squared. So only the x and x terms and the y dot y terms are going to survive. So you end up with r squared omega sine cosine with a minus sign for the x's and with a plus sign for the y's. And so they're just going to cancel. So r is always perpendicular to v. So from position we got velocity, and now of course we can get to acceleration. So acceleration, the same thing. We do another derivative. A of t is d dt of the velocity. And we only have the same terms here, cosines and sines appearing. We can use the same derivatives here for cosines and sines, and we will find minus r omega squared. Now this sine is going to turn into a cosine omega t x plus r omega squared. The cosine is going to turn into a minus sign, so we're going to get a minus here and the sine of omega t in the y direction. So that's our acceleration. If we look at the acceleration and the position carefully, we'll actually see that we have a cosine omega t x, sine omega t y, cosine omega t x, sine omega t y. Okay, that looks very similar. The only difference is actually just a factor minus omega squared. This is minus omega squared times the position vector. So the acceleration is minus omega squared times the position vector. The acceleration vector is minus omega squared times the position vector. And of course that also means that the magnitude of the acceleration is omega squared times the magnitude of the position vector. And that's actually something we just derived earlier. The magnitude of the acceleration vector, that's the magnitude of AC, right? That's omega squared times r. That's the term that we derived here. So we can derive or rederive this expression by going through the actual expression of the velocity and the acceleration to get to the expression that the acceleration is minus omega squared, or is proportional to the position vector. The acceleration is parallel to the position vector. Okay. So this is true as long as our time derivatives only, of course, apply to the sine and the cosine terms. As soon as there's a time dependence in omega, that is, of course, not going to be valid anymore. At that point, we're going to have to use the chain rule, and there's going to be additional terms that are introduced that are dependent on omega. So this is true when, and I'll just say only when omega is constant. So when omega is not constant, that's not going to be true. That is the case of non-uniform circular motion. Non-uniform, accidentally pressing the wrong buttons here. Non-uniform circular motion. So non-uniform circular motion is when omega is not constant, but omega is a function of the time. So if omega is a function of the time, let's look at that on our slides. If omega is a function of the time, now the velocity around this circle is going to be a function of the time. So the speed is not going to be constant. So v is going to be a function of the time. The speed is not constant anymore. And what I mean here is that v is the magnitude of vt. That will be a function of the time, right? So if the velocity is a function of the time, if the speed is a function of the time, if there's a change in if there's now a change in omega, that will give us additional terms in our expression for the velocity here, in our expression for the acceleration here. And in particular, what it will do is it will introduce in our general acceleration vector, it will still have a centripetal component, but it will introduce a tangential component as well. So this one is going to be proportional to the radial direction. This one will be proportional or along the tangential direction. So we'll have a centripetal component towards the center, and we'll have a tangential component that actually in some sense accelerates and decelerates and changes the velocity such that the speed changes and such that the angular frequency changes. So we're going to have these two components, a radial component and then a tangential component. And that's kind of indicated, oops, where is it? Here. That's kind of indicated here. So we have our centripetal component or tangential component. So in this case, will this particle be increasing in speed, or will it be decreasing in speed as it goes around the circle? So let's say increasing 1, decreasing 2. Okay, yeah, I see a few people increasing. Slowly the answers are trickling in. So in this case, it will indeed be increasing because the acceleration is along the direction of motion. So it's going to be becoming even, well, in some sense, of course, maybe the ones who are slow to react are actually the smarter ones here, because I didn't say that this particle is moving counterclockwise to begin with. It could be that it is actually moving clockwise, and if it's moving clockwise, then of course it would be decreasing in speed. So yeah, not enough information is given in this particular drawing. It was kind of assuming that the direction of motion was the same as in the previous drawings, so previous diagrams. So a couple other questions. So, can the um, can the centripetal acceleration ever change the speed of a particle? So who thinks the centripetal acceleration can change the speed of a particle in a circular motion? So indeed, yep, the centripetal acceleration, the component that is pointing towards the center, cannot change the speed. Um, the only thing that can change the speed of the particle is the tangential component to the acceleration. The tangential component is what changes the speed. The centripetal acceleration is what, in some sense, changes the direction. It changes the direction of the velocity vector to make it go around in a circle. The tangential acceleration changes the actual magnitude of the velocity vector. Okay, so this was all about uniform, non-uniform circular motion, and you know, we could go to a numerical example, but of course that doesn't necessarily change much. What we're gonna do is talk about relative motion now, which is what happens when we describe things in moving reference frames, or reference frames that move with respect to each other, which is going to be very important in particular because it will allow us, if we understand how to move, how to describe motion in different reference frames, it will allow us to pick reference frames and change from one reference frame to another, depending on what is the easiest reference frame to pick in. So first of all, what is a reference frame? It is where we pick the origin and in which direction we pick the x, y, and z axes. And we can, of course, pick that however we want. If we're describing, for example, the motion of someone on Earth, then we would pick x, y, and z fixed to Earth. If we're describing the motion of the moon around the solar system, then probably we would pick the origin at the center of the Earth as opposed to the surface of the Earth. If we're describing the motion of another planet, we might pick the origin at the center of the sun instead of the center of the Earth. In fact, we might not even pick the center of the sun because the sun and the planets are rotating around their center of mass. So we would probably pick the center of mass of the solar system. So there's different reference frames that we can pick. And some of them are moving with respect to each other. For example, the reference frame that is centered at the Earth is moving in uniform, close to uniform circular motion around the center of the sun. So it will be moving in uniform circular motion around or in the reference frame of the sun. In our case, we're going to only look at reference frames that are moving with a constant linear velocity. If we want to go to reference frames that are moving in a circular fashion, like the reference frame at the center of the Earth with respect to the reference frame at the center of the sun, then we're introducing acceleration. In fact, we're introducing exactly this kind of centripetal acceleration on the reference frames. And that introduces some additional effects that we aren't ready to get into and probably aren't going to get into until you get to the course of general relativity, which might be a few years from now. So for now, we're going to just look at reference frames that are moving with a constant velocity with respect to each other. One example that's given in the textbook is that of a person walking on a train. So a train going with constant velocity, and t is the train, p is the person, and e is the Earth in this expression here. So the velocity of the person with respect to the Earth is going to be the velocity of the person with respect to the train plus the velocity of the train with respect to the Earth. One helpful notational strategy is to make sure that you always say what is the thing that is moving, and with respect to what is it moving comes second. And then you can sort of contract these indices at the center, and the only ones that are left should be the ones on the outside. So if you have multiple terms, they should always be, the thing with respect to which you have this velocity should be the starting point of the thing that you describe the velocity of. So in this case, the velocity of the person with respect to the train, the velocity of the train with respect to the Earth, the sum of those vectors gives us the velocity of the person with respect to the Earth, or VPE. So if we look at that in a numerical example, if our train is going at 10 meters per second with respect to the Earth in the positive direction, if the person is walking, running at -2 meters per second with respect to the train, then that person will have a velocity with respect to the Earth that is 10 meters minus 2 meters. So the sum of those two vectors, the sum of the vector TE, velocity TE, and the vector velocity PT, actually, in some sense, of course, we do PT plus TE as described here, PT plus TE. That gives us the velocity of the person with respect to the Earth, and that's going to be 8 meters in this direction. So the two reference frames that we have here, the reference frame of the Earth and the reference frame of the train, give us a different velocity. The relative velocity is different. And of course, in this case, depending on what kind of problem we would be asked to solve for this person on the train, we might either pick the reference frame of the train or the reference frame of the Earth. Of course, the same thing will be true if we describe the velocity of the moon with respect to the sun will be the velocity of the moon with respect to the Earth plus the velocity of the Earth with respect to the sun. So in general, let me get back to the slides here. So relative motion the velocity of a point with respect to a reference frame S prime will be the velocity of the point with respect to a reference frame S plus the velocity of the reference frame itself in the new reference frame. So this is going to be the motion of reference frame S with respect to S prime. So this would be the motion of the train in the reference frame of the Earth, for example. And this is going to be something we're going to have to use a lot, and of course we can describe it as APS in accelerations. APS prime is APS plus ASS prime. But as I said, in most of our cases, or all of our cases, we're going to use ASS prime is equal to 0 for constant velocities VSS prime, which is the situations that we're going to consider. So the example that we looked at in the slides here is just in one dimension. Of course, we can make this a little bit more complicated by going to 2 dimensions, and then even more complicated, although then it doesn't change as much anymore, by going to 3 dimensions. So we could have the velocity of a car at 80 kilometers per hour going into the east direction. So this is the velocity of the car with respect to the Earth, VCE. Now we have the velocity of the truck that is coming from the north, that's going towards the south. It is VTE, the velocity of the truck with respect to the Earth. So what's now going to be the relative velocity between the two? Well, it's going to be V, for example, VCT, which is the velocity of the car with respect to the truck, is going to be the velocity of the car with respect to the Earth plus the velocity of the Earth with respect to the truck. So notice again how we put the same indices closest together so that we can sort of contract these indices and just have c and t left. So that's going to be the velocity of the car with respect to the truck. And we can calculate this, this sum component-wise, in this case in particular, because both of these have just an x and a y component. So we're going to end up with a magnitude of this relative velocity VCT that is just given by Pythagorean theorem, and it's going to be 80 kilometers per hour squared plus 70 kilometers per hour squared with a square root, right? So that's how we can use relative velocities to determine the magnitude of relative velocities, and of course we would be able to calculate the angle here as well. So we're going to stop with that, and next lecture on Friday we're going to probably do one more thing about this. Those of you who are sailors or who have sailed before may know about collision courses, and this is actually related to collision courses on sailboats. So we'll come back to that, and then we'll apply this to someone swimming across a river, for example. We can use the relative motion there as well. And then we're ready to move on to the next chapter. So that's it for today. So we'll pick this up on Friday, and I'll see you then. And I'll be hanging out here in Gathertown for another 10 minutes or so.